Hello everybody. Today we start with a new chapter in standard 10th physics ICSE, that is electromagnetism. That is the 10th chapter of Concise physics textbook. Electromagnetism is one of the most important chapters in your syllabus because it is worth almost 10 marks in the paper. In fact, not even 10 marks, more than that, because in the first section also there will be questions based on that, and then in the second section also there will be at least one complete set based on these electromagnetism. So that's why it is quite an important kind of thing. No numericals in this, but mainly there is diagrams and understanding of DC motor and AC generator and normal magnetism. So quite an important chapter. The transformer part is also there, but the transformer part for 2020 is cancelled because of COVID. So you won't be learning transformers, but yeah, the other part, that is the magnetic effect of electric current, the DC motors and its how it's working is going to be there, and the AC generator, how it works. We are going to see that part in this chapter. So we start with the first part of the chapter, so that is magnetic effect of electric current. Now it was found that when there is a particular wire, which is, suppose I just take a circuit, so the circuit is like this is a wire over here, and then there is a battery out here with a key over here, and then you are having some resistance over here, and if it is like this, so if you take this particular wire which is over here, and we know that this current is going to flow in this direction, it is going to flow like this, it will be seen that when the current flows through this thing, at that time, if I place a magnetic needle, okay, if I take a magnetic needle and place this magnetic needle somewhere here, suppose I place it over here like this, such that initially when the current is not flowing, it is showing me the not, so this is the not direction, it is showing me the not direction like this. So it is showing me the not, but the moment I switch it on, the moment I switch this thing on, it will be seen that there is a deflection of this thing, and instead of showing me the not so direction, it will be going like this, or it may be going like this, depending upon the different conditions. So there will be a deflection. Now we have studied earlier in the 9th science that the deflection in the magnetic field will be there only when there is another magnetic field available in that vicinity. So you can understand that when the switch was off, at that time it was showing me north south direction. That means there was no magnetic field around in that vicinity. But the moment I switch it on, there is a deflection which shows that the magnetic field has been generated around this wire, which is deflecting the magnetic needle. So this is what was done by Oersted. So Oersted did an experiment to prove that magnetic field exists in around a current carrying conductor. He done this particular kind of experiment. So let's go through the thing one by one. So first one is Oersted's experiment on the magnetic effect of electric current. Hans Oersted in 1820 in his experiments observed that when an electric current is passed through a conducting wire, a magnetic field is produced around it. Right? So whenever electric current is passed through a wire, then a magnetic field will be produced around that particular wire. The presence of the magnetic field at any point around this current carrying wire can be detected with the help of a compass needle. Note, in absence of any magnetic field, the needle of the compass can rest in any direction, but in presence of magnetic field, the needle compass rests only along the direction of the magnetic field. In the Earth's magnetic field alone, the needle rests only along the north-south direction. So when it is not having any other magnetic field other than the Earth's magnetic field, then the magnetic needle is going to rest in the north-south direction. But in the presence of any other magnetic field around it, the needle will deflect and show a particular, not a particular north-south direction, but something else. So let's see what he did in the experiment. In figure 1.10.0, AB is a wire lying in the north-south direction and connected to a battery through a rheostat and a tapping key. A compass needle is placed just below the wire. So let's see one by one what is the observation, what we see over here. So let me draw the figure exactly the same as what is given in the textbook, so that you are not confused about the fact that what is done by me and what is done in the textbook. So if you see over here, the figure goes this way, that this is the rheostat and this is the battery which is connected to a tapping key. Okay, the tapping key is there, and then there is this particular wire. So we have this condition like this, which, sorry, this is connected to a rheostat, so this will be connected to the jockey, right? So this is the plus minus of the battery, this is the rheostat, this is the tapping key, and we know that the direction of the north is in this direction. So this is the north, the geographical north is this side. So in this particular condition, if I place a magnetic compass under this wire, now this wire is named as AB, so the current is not flowing over here, and so we are the first condition, no current. Then the needle is going to show the north-south direction. So if I place a magnetic needle underneath, now because it is underneath, I am showing it dotted so that you can know that it was below, it is below this particular thing. So when I show it like this, it is below the thing, and it is seen that it is going to show me the north-south direction like this. Okay. Now the second condition is that I switch it on. So when I switch it on, so the second one is switch on. So when the switch is on, the current will flow like this, in this manner. So the current is flowing in this manner. Since the color flows in this manner, it is seen that this one will be deflected like this. Okay. So in that case, it is deflected upwards. So we can just say upward deflection, deflect upwards, right? Then what we do is we are changing the battery connection. So instead of giving the battery connection like this, we are having the connections to be like this. ये negative, ये positive यहाँ पे. So the current is going to flow like this. So the current no longer flows in this direction, but the current flows in this direction. So battery reversed. Then the deflection will automatically now go downwards. Okay, so deflection will go downwards. So this will be deflect, deflect downwards. Okay, that is one part. Now what we do is, we are going to do one more thing, and that is, we keep the battery as it is. We keep the battery as it was in the earlier condition. So we keep it positive, negative like this, so that the current can flow in this direction. It will be, and what I do over here is that instead of keeping the compass below the wire, I keep it above the wire. So if I keep the thing above the wire, so that means I I'm going to see like this, a complete thing like this. So I'll not be able to see the wire. When I place it above the wire, it will be seen the deflection is downwards now. So if I take the needle above wire, it will be deflect downwards. Okay, and if I am going to change the battery connections now, so if I change the battery connections to be like this, then it is going to be deflection upwards. So again, last one will be battery reverse. The deflection will be upwards. Got it? So you got these 4 conditions over here. पहले क्या किया? No current, no deflection. Direction of the needle north south. Current started. Then the if the needle is below the wire and the wind is switched on, the deflection upwards. Okay. If I reverse the battery, deflection goes in the opposite direction. Similarly, if I switch it off, it will be again steady with north-south direction. Then I place the needle upwards, above the wire. Instead of below the wire, I put it above the wire. When I put it above the wire, I'll see that the deflection will be ulta. Okay, जब भी मैंने इसको normal positive negative रखा, तो deflection instead of going upwards, it is going downwards. And when I change the battery, it is going upwards. So this is what was done in the experiment. So, observations. When the key is open, that is, no current passes through the wire, the needle points in the north-south direction along the Earth's magnetic field, with the north pole of the needle pointing towards the north direction. In this position, the needle is parallel to the wire as shown in the figure 10.1a. Second, when the key is pressed, a current passes in the wire in the direction from A to B, from north south to north, and the north pole of the needle deflect towards the west. So here we can say over here it will be deflecting towards, deflects west, and here it will be deflects east, and here it will be again east, and here it will be west. Okay, upward downward thoda confusion ho jayega. So it will be this way. When you switch it on, when you place it below, it will be towards west. When you place it above, the reverse it will be towards the east. If current in the wire is increased, the deflection of the needle also increase. Now, so here again, the important thing is, if with the rheostat, I am adjusting the amount of current which is passed through the circuit. If I increase the current, the deflection also increases. If I decrease the current, the deflection also decreases. So if the current is very high, it is going to be almost like बहुत ज़्यादा deflection आएगा. और अगर current कम रहेगा तो कम deflection करेगा. So the deflection towards west will be more if the current is more, and will be less if the current is less. When the direction of the current in the wire is reversed by reversing the connection at the terminals of the battery, the north pole of the needle points towards the east. So if I reverse these connections, instead of showing me west, it shows me east. So it goes downwards. Fourth condition, if the compass needle is placed above the wire. So if I place it instead of here, if I place it above the wire, the north pole deflects towards east when the direction of the current in the wire is from A to B, but the needle deflects towards west, where as shown in figure 10.1e, if the direction of the current in the wire is from B to A. Okay, so when it is from B to A, it will be towards the east, whereas towards the west, whereas it is from A to B, it will be towards the east. So that's exactly the opposite. So it is going to, and when I put it above, it will be deflection from A to B will be east, and from reverse करेंगे तो B to A will be west. So let's understand why does this thing happen. On passing current in the wire, a magnetic field is produced around it, and the magnetic needle of the compass experiences a torque in this magnetic field, so it deflects to align itself in the direction of magnetic field at that point. On increasing current in the wire, the deflection of the compass needle increases, which implies that the strength of the magnetic field around the wire increases. On reversing the direction of current in the wire, the direction of the deflection of the magnetic field of the compass reverses, because the direction of the magnetic field reverses. So inference, a current on or a moving charge produces a magnetic field around it. This is called as magnetic effect of current. The strength of the magnetic field depends on the magnitude of the current, and its direction depends on the direction of the current. So that is the main thing, that whenever a current carrying conductor is there, there will be a magnetic field produced around it. The magnetic field so produced will be such that it will be dependent on the more the current, more will be the magnetic field, lesser the current, lesser the magnetic field, and it will, the direction of the magnetic field will depend upon the direction of the current. Okay, so direction of current के ऊपर direction of the magnetic field will dependent on, and the strength of the magnetic field will depend upon the current, the amount of current passing through the conductor. Magnetic field and the field lines due to current in a straight wire. When a current is passed through a conducting wire, a magnetic field is produced around it. At a point, the direction of the magnetic field will be along the tangent drawn on the magnetic field at that point. The magnetic field lines can be drawn by means of iron filings as follows. So the same iron filings what you used to do earlier, कि paper रखा नीचे magnet रखा फिर iron filings करके tap किया तो वो round हो जाता. Similarly, here we are also going to use the same way. Like you can do it even in this case, that you are going to take a sheet of paper. Now you are going to take this wire in such a way. Okay, I'll take it over here. This is the standing line. So if I place a paper over here like this, and I sprinkle the iron filings over here, when I switch it on and tap it over here, you will find that due to the magnetic field, there will be concentric circles. The iron filings will arrange themselves in concentric circles around the conductor. Okay, so that's what we can see, that take a sheet of smooth cardboard with a hole at the center, place it horizontal and place a thick copper wire XY vertically through the hole, connect an ammeter A, battery B, rheostat RH and a key K between the ends X and Y of the wire as shown in the figure. Sprinkle some iron filings on the cardboard and place an electric current through the wire by inserting the plug in the key K. Gently tap the cardboard. It is observed that the iron filings were arranged along the concentric circles around the wire as shown in the dotted lines in figure 10.2. If a small compass needle is placed anywhere on the board near the wire, the direction in which the north pole of the needle points gives the direction of the magnetic field at that point, which is marked by an arrow in the field. So if I place a magnetic field, if I place a magnetic compass over here, if it is showing me like this, so that means the direction of the magnetic field is in this direction. So it is moving in the, we can see over here, when we take it over here, it will be clockwise direction. So we can see that the movement will be in clockwise direction if the flow of current is like this. Okay, if the flow of current is downwards, so anyways, you can see in the figure. So when the flow of current is downwards, and I have played over here, and the flow of current is like this. Okay, so if the current is flowing in this direction like this, then the field over here will be such that it will be seen clockwise. Okay. For the magnetic field line patterns, we know that the magnetic field lines form the concentric circles around the wire with their plane perpendicular to the straight wire and with the centers lying on the wire. When the direction of the current in the wire is reversed, the pattern of the elephant does not change but the direction of deflection of the compass needle gets reversed. So if I am passing the current now like this, then the direction of this compass will show this way. So the direction will be in anti-clockwise directions. Okay. So if you reverse the direction of the current, the concentric circles are not going to change. The magnetic field will remain the same, but the direction of the magnetic field is going to change. That means it is going to go in the opposite direction. Instead of going clockwise, it will now go anti-clockwise. The north pole of the compass needle now points to the direction opposite to the previous direction, showing that the direction of magnetic field has reversed. On increasing current in the wire, the magnetic field lines become denser and the iron filing gets arranged in circles up to a larger distance from the wire, showing that the magnetic field strength has increased and it is effectively up to a larger distance. So yes, first thing is that if you are increasing the current, the concentric circles will be there, but the area where the concentric circles can be there will be greater, because that just shows that on increasing the current, the magnetic field is becoming stronger and it is at it is going to be there for a larger distance. Note the magnetic field at any point is the combined effect of the magnetic field due to the current in the wire and the magnetic field of the earth. At points near the wire, the magnetic field due to the current in the wire predominates, due to which iron filings arrange themselves in circles, while at point far off from the wire, the magnetic field due to the earth becomes more pronounced as compared to the magnetic field due to the current in the wire. As a result, iron filings tend to arrange themselves in straight lines. The point where the two fields are equal and opposite is called as a neutral point. At the neutral point, the resultant magnetic field is zero and the compass needle at this point rests in any direction. So it should be known over here that when we are taking this current carrying conductor, this current carrying conductor is going to have a magnetic field around it. At the same time, there is also going to be the magnetic field due to the earth's magnet. Okay, the earth's magnetic field also will be present in this particular location. Now, in such a condition, because the magnetic field of the conductor near it is going to be much stronger, so the magnetic needle, if we place it over there, will be deflected according to the magnetic field of the conductor. But if I place it a bit further off, you will find that the magnetic field lines, or you can say the iron filings, they will not be in concentric circle, but they will become parallel then. Why will they become parallel? Because at that point, the magnetic field of the earth magnet is coming into effect and not the magnetic field caused by the conductor. And that shows that instead of being in concentric circles, it will be parallel lines. So the parallel lines indicate that it is the earth magnet, and it will be seen that the point where the earth magnetic field starts and this ends, that particular the distance between these 2 points, the small area between these 2 points, is called as the neutral point, wherein the resultant magnetic field due to the conductor and the earth is zero. And if you place a magnetic needle near there, it will just rest in any direction. Okay, neither north south nor ऐसा कोई भी direction में वो रुकेगा. Now, rule to find the direction of magnetic field. Now, of course, we have seen that, okay, we just say that, okay, it will be clockwise, it will be anti-clockwise, but why is it so? The main thing is that, why or what will be the method by which I will find out, okay, वो clockwise जाएगा कि anti-clockwise जाएगा, okay? So, the rule for this is the right hand thumb rule. So, experimentally, the direction of the magnetic field at a point is determined with the help of compass needle, but theoretically, the direction of the magnetic field or magnetic field lines produced due to the flow of current in the conductor can be determined by various rules. One such rule is right hand thumb rule. So yes, here we put the magnetic field, the needle, and saw the direction of the north, and that's why we say that it is going clockwise or it is going anti-clockwise. Oh, so we just found out that way. But if I am doing it theoretically, where I'm not doing a practical thing, then how do I find out? I can find out by a rule which is called as the right hand thumb rule. So what is the right hand thumb rule? We hold If we hold the current carrying conductor in our right hand such that the thumb points the direction of the flow of current, then the fingers encircling the wire is in the direction of the magnetic field line. So if I consider that this is the direction in which the current is flowing, okay, we consider the direction of the current is like this. If I see the direction of current like this, so I will hold this particular current carrying conductor in my right hand. This is my right hand. In my right hand, in such a way that my thumb is pointing the direction of the current, then the curved lines over here, they will give me the direction of the magnetic field. Okay, so in this case, if I am placing it like this, when the current is flowing like this, it is curved like this. So you can see I have shown the red colored arrows like this. Whereas when we took it from up to down, at that time it was going to be clockwise from up. So then what happens, this is going to be held like this and I am going to hold it like this over here. The current is going to flow downwards and then you can see that the ring is over here like this. You can see this, it is going like this. Okay, it is going like this. So here it is coming in clockwise. So from here it is clockwise direction. So that's how we can see that if it is going to be if I hold the current carrying conductor in my right hand such that my thumb is pointing the direction of the current, then the curved fingers are going to give me the direction of the magnetic field. In figure 10.3, the direction of the current in the conductor XY is upwards. The magnetic field lines are anti-clockwise around the conductor. The magnetic field due to a current in a loop or a circular coil. The magnetic field lines due to a current in a loop can be obtained by following experiment. Experiment: take a thin piece of thick wire or bent in a form of a loop or a coil. It is passed at 2 points P and Q through a horizontal cardboard C such that the points P and Q line the plane through the diameter of the coil. Then sprinkle some iron filings on the cardboard. Connect a battery through a rheostat and key between the ends X and Y of the loop as shown in figure. Close the key to pass the current through the coil and tap the cardboard gently. It is noted that the iron filings can get arranged in a definite pattern representing the magnetic field of the current carrying loop. To find the direction of magnetic field lines, the compass needle is used. The direction of the magnetic field at the point is along the needle in the direction in which the North Pole points. Okay, the needle will be in the North Pole point. An arrow is marked on each magnetic field lines to indicate the direction of the magnetic field. So what exactly is done is, suppose I take a coil. Now instead of just a conductor, I am taking a coil. So I have got a particular paper. This paper is over here like this, and I have got two holes over here, and through that passes a current carrying conductor which is going to be like this, which is connected to a battery. I'm not showing this circuit over here, I'll just show you the battery over here. And this is connected like this. So it is going there, यहाँ से अंदर से आया ऐसे और बाहर गया, and it is coming like this. Now in such a case, you can see that, let's not talk about the compass needle. I'll just take it as per the right hand thumb rule. So if I know that the current is going to pass through like this, when the current passes like this, and I'm holding this thing like this with direction over here, so this is going to be curved like this, so it will be like this. So here we can see the direction of the magnetic field will be like this, so curved like this, so it will be in this direction. So you can see it will be arrows going like this. Now let's say this one, I'm going to hold it downwards because the current is going to pass like this and going to go downwards. Of course, the magnetic field will be in circular pattern only, in the same way as earlier. But now I will see, because it is going downwards, so curved like this, so it is going to go give me the arrows in this manner. So we can see the arrows are in some like this, that they are parallel at a particular center, right? So this is how you can find out the direction of the magnetic field. From the pattern of the magnetic field lines, it is noted that in the vicinity of wire at P and Q, the magnetic field lines are nearly circular. Yeah, so over here and over here, it is nearly circular. Within the space enclosed by the wire between P and Q, the magnetic field lines are in the same direction. So you can see within the two wires, this is in the same direction. All of them are in the same direction. Near the center of the loop, the magnetic field lines are nearly parallel to each other, so the magnetic field may be assumed to be nearly uniform in a small space near the center. At the center, the magnetic field lines are also along the axis of the loop and normal to its plane. So here it is, the axis of the loop and they are perpendicular and normal to the plane. And the magnetic field lines become denser, that is, the magnetic field lines increases if the current in the if the strength of the current in the loop is increased and the number of turns in the loop is increased. So this is a very important point, that to increase the current or to increase the magnetic field over here, you are either increasing the current passing through it, or you are having more number of loops over here. If I have more number of loops over here, then also my magnetic field is going to increase. So I can increase the magnetic field by two ways. One is by increasing the current, or I can increase the number of turns in the loop. The magnetic field lines through the loop is in same direction. They appear to come out from the face of the loop on other side, so that face becomes the north pole, while the magnetic field lines appear to enter in the front face of the loop, so it behaves as a south pole. Thus, the loop acts like a dipole and has a magnetic field similar to that of a magnetized disc of radius same as that of the loop. So you see that the magnetic field lines pass to the loop in same direction. So magnetic field my lines is going to pass the loop in. So you can see it's all in the same direction. So the face behaves as the north pole. So this face behaves as a north pole, and while the magnetic field line appears to enter into the front of the face. So while the magnetic field lines appear to enter in at a front face of the loop, so it behaves as the south pole. Anyway, so when you are seeing this thing, you are consider this as a sheet which will be having a north pole at the top and south pole at the bottom. The polarity of the two faces of the loop depends on the direction of a current in the loop. On reversing the direction of current in the loop, the polarity at the face of the loop gets reversed. The polarity of the face of the loop is determined by the clock rule. So what is the clock rule is? Clock rule or clockwise current, that is south pole, and the anti-clockwise is north pole. Looking at the face of the loop, if the current around the face is in the clockwise direction, the face has the north polarity. While if the current at that face is in the clockwise, in the anti-clockwise direction, then it is the north polarity, and if it is in the clockwise direction, the face has the south polarity. So if I see that, suppose I have got this particular thing and the current is such way that the wire goes here, it goes here, goes here, goes here. So front back, front back, front back, front back, ऐसे करके वायर जा रहा है. So you can see the current is flowing in this direction. So when you see this part over here, so what you can see that this is moving in the clockwise direction. Because it's moving in the clockwise direction, so this part over here becomes the south pole. So this thing over here like this, so it is south pole. Now the same thing I'm going to change the thing over here. So you can see it is the same thing. Now from this side, you are feeling that this is going in the anti-clockwise direction. So this is the north pole. So you can see that when the current is entering into a particular, so when the current is passing into the coil, if you can see that अगर हम लोग current देख रहे हैं कि it is going through in a clockwise direction, then the face where you can see it is a clockwise direction is the south pole, and the other part is the north pole. And if you see it is an anti-clockwise direction, then that is the north pole and the other part is the south pole. So this is how you can determine the polarity of the. So the current at the face of the loop is anti-clockwise, so it behaves as a north pole, while the current at the face of the loop is clockwise, so it behaves as a south pole, which is very clearly given in the figure 10.5 A and B. Okay. Now we move on to the next part, that is magnetic field due to current carrying cylinder, coil or solenoid, in the next video.